Formally welcome you all to the Woodrow Wilson Center. My name is Kent Hughes. I run a program here at the center on science, technology, America, and the global economy. People hear that once and then quickly refer to it as STAGE, so that's the welcome acronym. I want to extend a particular thanks to the Hewlett Foundation, who has helped sponsor today's program with a generous grant, and also to thank the United Nations University, a very interesting institution that you all may not be familiar with. The UN University has helped us work with Professor Steve Kresovich, who I'll introduce in just a moment. Let me just say a bit about the UNU system. It is something of a think tank for the United Nations, and at the same time meant to be a gathering place for scholars around the world. The headquarters of the United Nations University is in Tokyo, but there are 14 research and training centers scattered around the entire world. They work on a series of multidisciplinary projects that really go from this question of biofuels to urban development to the role of bilateral trade agreements in the New World. It is an institution I think you all will be hearing more about in the future. Before I introduce our panel, I wanted to just say a word or two about the Wilson Center for those of you who are new or those watching via the webcast that are not familiar with the center. We were established in 1968 as a living memorial to Woodrow Wilson. As you may know, Wilson was the only American president to have earned a PhD. And Congress really gave us the assignment of bringing those two worlds together, in a sense, the thinkers and the doers, the people that are really making policy together with the people who are doing some of the best thinking about public policy. And that's very much the kind of assemblage that we have on today's panel, people really who in many ways capture both sides of Wilson's life. I'm going to introduce our panelists in the order in which they're going to speak, and they will speak for varying lengths, but we're going to leave lots of time for questions. To my far right and your far left, we have Stephen Kresovich, a professor in the Department of Plant Breeding and Genetics and Plant Biology at Cornell. He has a host of roles there. He's the Associate Vice Provost for Life Sciences, and in that role is responsible for a university-wide leadership for Cornell's new Life Sciences Initiative. This is the largest ever cross-campus-wide initiative at Cornell. He has a very, I'm not going to be too long in these introductions because you have the bios in front of you, but he has a very distinguished academic background and served on many commissions, and including his link to the UN-supported International Agricultural Research Centers. Not quite as far to your left is Steve Hutchinson. Steve is a professor at the University of Maryland, again with a very distinguished record of publications and academic research. But he is taking a step into the private sector. He is, let me summarize this, if you correct me if I've got it wrong. He's discovered a bacterium in the Chesapeake Bay that's extremely efficient at turning cellulose into a kind of sugar that could easily be translated into ethanol. And he is the founder and CEO of Zymetis. Is that a company that is working on seeing if this can't be scaled up. And not nearly as far to your left and to my immediate right, I'm delighted to introduce Paulo Sotero. Paulo is a colleague here at the Woodrow Wilson Center. He runs the Brazil Institute. For many years, he was the Washington correspondent for the Estado de São Paulo newspaper, a kind of a combination of the New York Times and Washington Post for Brazil. He is one of these rare people that knows two countries extremely well. Some of you who are as old as I am will remember Alistair Cook, who used to be a translator of English culture for the United States. And Paulo really has that kind of facility with regard to Brazil. He and I have done a good deal of work on Brazilian innovation, with much of it focused on the biofuels question. Let me call then on Steve Kresovich to start us off, and he's promised to, as a special treat, to use PaperPoint rather than PowerPoint this morning, and then we'll move to Steve Hutchinson and Paolo.
Thanks, Kent. Welcome, everybody. First of all, I find this to be a real liberating experience. As a biologist, my training is also in genetics. PowerPoint is like my crutch. So when I heard there was an opportunity to not use PowerPoint, I thought it would be an interesting challenge today. Also, I teach at Cornell, and I try to grind the students out. And if I see you using electronic devices or your phone goes off, you're out of here. Okay? Maybe after my 15 minutes are up, you can do what you wish, but at that point, we'll see. Okay? So that's some of the ground rules. I'd like to talk a little bit about my background. The first job I had was with Battelle Memorial Institute in 1977. I started on a project that was funded by the Department of Energy, and it focused on carbohydrate crops and sugar crops as a source of ethanol. So that was 1977. 1982, I went back to school and finished a dissertation, and the title of my dissertation was Sweet Sorghum as an Ethanol Source for Midwestern Cropping Systems. That was 1982. Then the price of oil changed, and I had to find a new focus for my research. So I primarily focus on conservation and use of agricultural genetic resources. So I'm particularly interested in the broad diversity of crop agriculture and the materials that we use in crop agriculture. I work nationally and internationally. Strangely enough, things have come full circle. I have a student that's graduating this May, and the topic of his dissertation is employing genomic tools for better understanding and breeding of sorghum as a potential source of energy. He has tools of bioinformatics, he has tools of genomics, he has advances in plant breeding, he interacts with engineers. He's way smarter than I am, and his dissertation is way more interesting than mine was. And that's the evolution of what's going on. So that's background. Biology is complicated, and there's no one single fix. And I'll come back to that a number of times through the course of the presentation. I was also intrigued when I saw the title. Scientists are skeptical by nature, so coming to Washington and wondering about what's going to go on in this room. Betting on biofuels is the title that was settled on. So betting. Kent, why betting?
I have to confess that it meant to convey a message that to some extent that we are placing some significant bets on biofuels. And being of Welsh descent, I have an absolute compulsion to choose alliteration.
You get credit for that answer. I'll think about exploring or optimizing biofuels, and I'll present it from a biological context. So let's start out with some general thoughts. Bioenergy offers new potentials for sustainable development, but also carries significant risks. Number two, the link between bioenergy growth and food security is complex, and I expect in the later session that this will be addressed in a more rigorous fashion. But we can talk about it from a biological context during my time. Third, the choice of location, feedstock, and production methods have significant implications for energy production and greenhouse gas balance compared to fossil fuels. And number four, some of the challenges posed by biofuels development are not new and mirror those related to agriculture and natural resource management in general. Okay, so with that as background, I want to go through a few other key ramblings or key points before I talk about the biology and genetics of feedstock development. First of all, I think it's fair to assume that few biologists think there's a silver bullet or panacea to biofuels. Production must complement conservation advances. both in the environmental sense and in the utilization of the energy itself. By nature, biomass is diffuse. There's material that's low energy that needs to move and be processed in a particular way. As a biologist that has an interest in this area, I'm particularly concerned about the bad press of maize to ethanol. And I'm not going to comment about that, and I suspect that'll come up later. David Pimentel works at Cornell, and he's a noted critic of energy balances in corn ethanol. He's at Cornell. As Vice Provost for Life Sciences, the good news is my constituency is 700 faculty members. The bad news about my job is my constituency is 700 faculty members. There's no agreement. It's not monolithic, and there's plenty of assumptions that are made in these type of analyses. So I enjoy good discussions on these. I think it's important that the short-term considerations of maize to ethanol don't blur what biology can contribute in the long run. Biology linked with environmental sciences, effective engineering and processing. And I don't think anybody should throw the baby out with the bathwater. Also, as a biologist and a person that's interested in diversity, I see a lot of inertia in the system. There's significant resources invested in the public and private sector to make maize into just about any possible product, also to make soybean, and there's good reason for that. However, as one looks at potential new options of biological feedstocks, there's an energy of momentum that we need to overcome if they're going to even be fairly considered. So that's an important thing. Generalizations are easy to argue and are doomed to failure because biological systems are very complex. And generalizations tend to be wrong. Regionalization is important. There's no one silver bullet. What may work in Texas, where they produce sugarcane, is not the same answer as in central New York, where we have water from the Finger Lakes and surrounding areas. It may not be the same as Iowa. So regionalization and thinking strategically for businesses and the science to be regional is very important. We need new science and new industry. There's a lot of research that needs to be done. We're just scratching the surface, and actually, to be honest, as a grantee from both the USDA and Department of Energy, I find an inordinate amount of discussion on a really focused topic where there's actually a lot of exciting things that are going on in the research domain that you all need to be aware of. And a little digging goes a long way to look at other things to compare and contrast to the systems that are in place. Research is essential. We talk about feedstocks, transportation, conversion, environmental effects. Off-the-shelf technologies are only a short-term solution, if a solution at all, and much work needs to be done in all those particular areas. And research in this area is going to take time, and when I go through the examples of plant breeding and genetics, you'll get a better understanding of that. Also, we need an iterative approach. I see down at the end of the table is my friend Larry Walker. Raise your hand, Larry. Larry's in the Department of Biological and Environmental Engineering, and Larry's actually one of my stakeholders. So I do breeding and genetics and look at crops, but I need Larry as a stakeholder because Larry works in conversions and conversion processes. So I need him on a daily basis to say, well, I need a little more of this, or I need a little less of that. And can you get it in this density, or how are we going to harvest that? So the iterative process between biologist, engineer, economist is essential. When I worked at Battelle Memorial Labs in the late 70s on the energy project, I was a biologist. In the office next to me was a chemical engineer, and an ag economist was in the office adjacent to him. And we used to wrestle, and the wrestling was really quite healthy. So the interactions and the iterative steps between the disciplines is critically important. And there needs to be point-counterpoint. I think Larry needs to argue certain things with me, and likewise, I need to try to convey messages to Larry that either this is going to happen or not going to happen. So iterative work between groups is really healthy. So with that, I'll go to the next section on science and plant breeding and genetics as it relates to biofuels. Let's talk about conversion of solar to chemical energy. Does anybody have an idea of how efficient plants are at converting solar energy to chemical energy? You know, you could get extra credit if you're close. Anybody want to offer an answer? Go.
2% maximum for sugarcane at the equator.
Okay, that's in the ballpark and probably based on the assumptions, but it's relatively low, isn't it? So we have what we have is an inefficient collector that's extensive. And what implications does that have? It has a lot of implications. So for example, relative to solar collectors, the efficiency may be 10 to 20%. So again, by nature, our system is diffuse. We need to recognize the implications downstream of the diffuse nature of the biological resource. Okay, let's talk about crop breeding a little bit. So maize to ethanol, why does it work and why doesn't it work? Okay, you have extra credit, so you're set for the rest of the presentation. Anybody else? Why does maize work or why doesn't it work? What are the criticisms? Go ahead.
Change of 30 starches that can be broken down into sugars.
Okay. Others?
It doesn't work because you have 30 starches.
Okay. Other comments? Well, crops are bred for specific uses. How long have we bred hybrid maize? Since the 30s. And what's been the goal of maize breeding?
Yield.
But what's the end product? Who are the stakeholders for maize? What do they do with maize? They feed it to animals, right? So what do we want in maize as an animal feed?
Energy.
Energy and nitrogen. Try to breed high nitrogen. It's not easy in a cereal, but there's intense selection for yield and nitrogen in the plant. So when somebody goes out and looks at a study and tries to fit something to a particular analysis of a system in place for making a biofuel, these things need to be considered. There are probably in the National Plant Germplasm System, that's the national system that maintains the national collections for crops around the United States, there are probably 20,000 entries or individual lines of maize in the national collection maintained at Ames, Iowa. And a lot of them are wild relatives, weedy relatives, and things that are called land races, materials that were grown historically in different cultures and brought back into the United States for desirable traits and different uses. We're barely scratching the tip of the iceberg in exploiting maize. And I'm not going to say we need to exploit maize, but the maize that's being converted to ethanol now may not be the exact type that you ultimately might want for production. As technologies change, as transportation system changes, and as demands change for whatever the ultimate product is. So crop breeding is really specific. Plant breeders have worked hard to develop a type in mind, whether you breed for soybean or maize or apple. You know, think about apple. It's like that octagonal red delicious for years and years and years. Well, what happens when you go to the market now? Granny Smith, Gala, Fuji, they don't look like the classic red octagonal cardboard tasting red delicious that everybody buys. So there's plenty of opportunity to adjust the material if it's done in a process where we think about uses, environmental implications, and biological potential. But it does take time. We need participatory breeding. I highlighted this before with the relationship of Larry Walker and I. You around this table as stakeholders need to be involved in this process. For the longest time internationally, plant breeders made progress with developing new crops, but it was at the expense of cultural changes in particular areas. And not that progress wasn't made, but progress was made by really changing the system. Now things work more effectively when scientists interact with stakeholders and the public in general so that we could work together and there are no surprises. Because if it's going to take me 5 to 15 years to breed a crop, when it comes out, I want it to be taken up and utilized. So there's this time lag. The implication in the time lag is you better have the right participants up front to help you think through what you're breeding for. So time and expectations. I said 5 to 15 years. What if you work with short rotation trees? How many years will that take? It's going to take more than an annual crop. And in perennial crops, sugarcane or tree species, growers tend to make their money in the regrowths, not the first crop. If you can keep your crop disease-free and healthy and you don't damage it when you harvest it, the incremental gain in subsequent harvests is really important. So I can tell you, when I did sugarcane breeding at Texas A&M, it would take me 15 years to release a variety. There's a popular apple in New York. It's called Empire. It was released in the last decade, so say 2000. Empire was bred. The cross was initially made in 1945. So agriculture takes time. There are ways to speed it up by using multiple environments. What plant breeders do, we use a northern hemisphere environment, and then when the weather's cold here, we have test plots in southerly locations. So it's important to get multiple generations in the shortest amount of time. So to have a good breeding program, there are two elements that you need. Understanding genetic diversity. There's genetic diversity in this room. How much genetic diversity is here? When I teach my conservation biology classes, I talk about Noah. Was Noah a good conservation biologist? There's some people here, as I looked at the list, they must have opinions of Noah was a good conservation biologist. Was he? I mean, I don't think Noah was. He did good things, but if you only take 2 individuals per species into your ark, that's called a genetic bottleneck. And you don't have much diversity that goes into that ark. So as a biologist, I'm a little skeptical of that story. So conservation biology and effective use of genetic resources requires a really good understanding of genetic diversity. And as I indicated, there are 20,000 maize lines in the national collection. In the international collection, which is maintained in Mexico, there's probably another 20,000. I work with sorghum as one of the organisms I work with. It's a grain crop native to Africa. There are 40,000 entries in the national collection maintained in Griffin, Georgia. None of that has been exploited. None of that has been considered for biofuels. None of that has been even grown out and looked at. It's just too much material and finite resources going into that. But implicit in the biological front end, we need to understand genetic diversity. Second of all, we need to employ every tool that we can. My student uses computational biology, genetics, genomics, advances in plant pathology, advances in agronomy, advances in chemical engineering, statistics. Using those tools really helps towards breeding an end product. So it's a multidisciplinary endeavor. So whether it's an individual working in a network of people or an individual investigator with multiple skills, we need to know a lot in plant breeding. So what are the targets? Ultimately, it gets down to what are the important criteria for a breeder or a geneticist to look at for traits for energy production, or traits for food production, or traits for both energy and food production. It's complicated. Basically, it boils down to, ultimately, as you indicated earlier, you have X amount of carbon. You talked about a conversion efficiency of 2%. What would happen if we could go to 3%? You said theoretically we could only get to 2. Maybe if that's the theoretical limit, maybe we're at 1.5 or 1.3. But the incremental gain there is significant because of the extensive nature of the resource. So in a breeding program, the first 3 criteria for breeding for biofuels is number 1, yield, number 2, yield, and number 3, yield. And why that's so important is we need to have an energy source as dense as it could be. Energy per unit input or per unit area and per unit time. So yield is really important, but there's a lot of other things. Another thing that's important is called harvest index. It's how much of the material is the harvestable product. And that's going to be a discussion when we talk about environmental concerns. How much do you need to leave back on the soil to maintain soil structure? So harvest index and the ratio of harvestable material to total carbon on the land is important. The Green Revolution is based on changes in harvest index. They used to grow wheats and rices that were very tall. They grew them shorter stature. What benefit did that have? First, the materials didn't fall over and lodge. And second, that carbon that was used to produce a stem now is converted in energy to go into the grain. So harvest index, it seems really simple, but that's an important one. And again, going back to maize, think about maizes that are grown for silage production. They can be 12 feet tall. If they don't produce grain, you have a lot of leaf material and it's going to be utilized, and it could be considered for biofuels. But there are types that don't look like any maize you'd see in Iowa that might be candidates. I don't know. Composition, end products. Larry and I work closely on this. I don't know what end products he wants. All I can do with the diversity of the material I work with is say, I've got these ranges. And if I've got this amount of lignin or this amount of cellulose or this amount of hemicellulose, how do I change that composition to what he desires as an end product? And they're interactive. They don't work independently. So in some instances, when I affect cellulose composition, it might impact on lignin or hemicellulose. So it's a complicated interaction of multiple genes affecting multiple constituents of the plant material. So composition is really important. Perennial regrowth potential, whether it's for providing the growers with opportunities to not have to replant and energy and financial costs associated with that, or maintaining cover on the soil for environmental reasons. Perennial growth and regrowth potential are very important. High water use efficiency, high fertilizer use efficiency, architecture. If I could produce, the good news for me would be, say I could get 20 dry tons per acre of whatever species I was growing. That would create quite a challenge for Larry Walker and his friends in harvesting and how they harvest the material. I've worked in sugarcane breeding and I know what moving material in and out of a field takes when it's very, very high tonnage like you'll see in Brazil. So good news for me of 20 dry tons per acre creates a lot of challenges for other people in the system. And architecture is very important. So to keep the plants upright, so during the season they take a lot of energy or intercept a lot of energy with their crop canopy, their leaf canopy. That's great for converting solar energy and ultimately to get in there and get the material. And also lastly fits the cropping system, the right maturity, disease and insect resistance. I mean, as a breeder I also have two implicit assumptions. One is oil's $300 a barrel and people are paying the real price for the cost of water. It takes me 15 years to do things. I don't know what the price of oil is going to be. Okay, so in summary, there are pluses and minuses to understanding diversity. The good news is I have 40,000 accessions to look through for sorghum. The bad news is I have 40,000 accessions to look through. And then ultimately, how do I put those combinations together in a meaningful way that the stakeholders find the material useful? There's great potential that exists, and the incremental difference in conversion efficiency from 1.3 to 1.5 to 2% is significant because it's so extensive. However, the extensive nature of the resource creates problems with logistics, harvesting, moving material. And again, I don't want things that are in the press now to preclude me from being creative and self-critical about the biological research I can do in the future to contribute to this area. So much research is needed, and it would be a shame that strong, intense debates over short-term transitional things move us away from really looking at long-term gains in this. And ultimately, systems approaches and interdisciplinary teams are essential. So with that, I'll stop and turn it back to Kent. Thanks.
And I appreciated that optimistic assumption about only $300 a barrel for oil. Steve.
All right. So I have a couple things that cause me to have to use a crutch called PowerPoint. One is that I am, even though I'm on leave, a college professor, which means that I have to have something to help guide me along. All right. The other is I give 2 to 3 talks a week. Each one's a little different, and so I need a crutch to tell me what I had in mind. So anyway, what I want to talk about today is really what are you talking about in terms of biofuels? Why biofuels? What's the opportunity? What are the problems that are preventing this industry from developing, and where we're going in the future? As Kent pointed out, I wear 2 hats. I'm professor of microbiology at the University of Maryland. I'm on leave to take a job. I've actually just had a title change. I've gone back to something a little more conventional called a chief technical officer for the company. I'll talk to you a little bit more about that later. All right. So where we're at right now is we have more than a 100-year history of driving automobiles. We've always driven those automobiles based on gasoline, but that wasn't the original idea. The reason I'm showing a Ford here is Henry Ford actually was the original person to suggest a biofuel to run vehicles. The thing, and the reason I'm starting out here is this sets the scene for what biofuels are all about, and because it's the scale. In the United States alone, we go through, to make this a little easier number to think about, 150 billion gallons of gasoline a year. Think about what that would represent in terms of a volume and the scale that's needed to cause some kind of displacement in that use. The reason that you want to displace that use has to do with, first of all, everything that we're aware of. I've used this slide for a while. It used to be, this was the 2007 number, and this is around 305 a gallon. If you are buying regular gas, this is the 2008 number so far. It's about 350 a gallon, and it's going to be up about here probably by the end of the year. Clearly, we're on a steep upward trajectory. Yet, now this is having a huge impact on us because it's, the issue is the supply and demand, and it's impacting our trade imbalance. And someplace in excess of 60% of our trade imbalance right now is due to the importation of oil. So there's the economic side of things. If I can operate the machine. There we go. Hopefully. I'm a Mac person. It's a handicap. There we go. All right. So we're dealing with extremely high gasoline processes, and we're also dealing with environmental impacts. All right? Believe it or not, this is a slide that showed up on the internet about 3 years ago. You can imagine what they're saying now. All right. So if you look at petroleum, petroleum is, in one sense, a biofuel. It started out as carbon dioxide in the air. There were some microorganisms in a lake. This is the current model. They converted it to an oil. That ended up in a form of biomass that settled to the bottom of the lake. You have geological processes that captured that, and you ended up with petroleum that now you can harvest and refine. All right? Took about 300 million years to accumulate the petroleum that we have here. We're burning it at the current rate of 1 million years worth of accumulated biomass in 1 year. Just to power this material. So we've gone through, in the last 100 years, in excess of 100 million years of accumulated biomass. Now, the analogy that I want to tell you is, think about taking a deep breath, holding your breath for 300 million years and exhaling. And that's what we're doing here, and that's why you're having an environmental impact. That environmental impact comes in a variety, if I can get this. Let go. One more time. All right, we'll do it the hard way. All right. So here what we have is oil production in the world. All you have to do is look at this little curve right here. This was a little hiccup in about 1980. This is about 2008. So these are the projections for what we have for oil production. We clearly hit the maximum, and from now on it's going to drop off. Why? Because we've simply consumed a lot of that oil. We're having to go to alternative sources for that oil, like oil shale and the like. All right? This is hydrocarbon use, and you'll see it's on an upward swing. What's wrong with that picture is you're going to have supply and demand problems, and you're also going to have an impact. All of that stored carbon dioxide showing up in the atmosphere. This is the year 2000, and we'd seen a 22% increase in my lifetime. It's now up to more than a 25% increase just in the last 8 years. This is a phenomenal rise in CO2 in the atmosphere. It's a major greenhouse gas, and even though it hasn't been terribly warm here in the past few days, if you look at it globally, you can look at temperatures and see them going through the roof. Now, the biofuel carbon cycle is something that's a little shorter. You're taking carbon dioxide out of the air, you're converting it to some form of biomass that you can harvest. You can take that biomass and it's conversion technology, and there's a whole variety of biofuels that you can run into. Bioethanol, biodiesel, biobutanol, biomethanol. They're all different compounds that are all derived out of a biomass process. The beauty on this is it's a one-year cycle. You've taken your breath, you've converted it into something that you can use, and then you're exhaling it. So that significantly shortens the carbon cycle, and because you're taking CO2 out of the air, it has much less of an impact. The Achilles heel for biofuels is land use. Now, those of you that are specialists in this can come up with all sorts of different categories how to use land use. I'm talking here about human activities, be it structures, factories, houses, roads, whatever. That's one use that we're all aware of. Food is what we were talking about just a few minutes ago, and it's a very important application. We have native habitats. I chose this just because it was a pretty picture and not for any other reason. And then finally you have fuel applications. And this is where the issues come up in the press right now, is the fact that really what you have is you can use your agriculture to produce food, or you can use your agriculture to produce fuel, and that's the present situation. Now, the beauty of some of the alternatives coming up is that you can actually use the land for two purposes, and I'll talk about some of those applications. All right. What we've been doing for the last 10, 15 years is taking some form of primarily starch, although Brazil has done an excellent job of taking another sugar called sucrose and converting that into ethanol. Now, I'm a biochemist, so I'm not going to give you a whole bunch, but you're going to get some along the way. So you're going to take sugar molecules, which are these little hexoses here, the 6 carbon components. They're linked into a polymer. You're going to break it up into constituent sugar using enzymes. You're going to ferment those using yeast. This is a 4,000 to 6,000 year old process. And then what we do is concentrate it. This is no different than making bourbon, all right? Except that you're going to take out all the water, and the end up is that you're going to get ethanol. And the yield you get is about 89 gallons of ethanol per ton of material, and it yields, depending on where you are, about 375 gallons per acre. This comes back to that land use issue. All right. Now, here's the problem, is currently we go through someplace around 2.8 billion bushels of corn. There's a whole bunch of facilities out there with more showing up every day. And we're producing about 7.5 billion gallons. In the next year or two, this will double. All right? So the end result is we're going to end up being able to produce about 15 billion gallons of ethanol. And this is where it's going to be capped by the current energy bills. All right? The problem is that in the U.S. you make about 13 billion bushels of corn. Gives you a theoretical yield of about 35 billion gallons. This is only about 23% of fuel use. That's if you take the entirety of the corn crop, and as we pointed out, there's lots of other uses for that corn crop. The real debate that's shown up in a whole series of editorials in recent days is the food versus fuel debate. There's clearly an impact of converting fuel, food to fuel. I have some issues with that, but it's been a very valuable process because this industry wouldn't exist without this process right here. It's critically important. And the other debate that was pointed out was the low energy gain. And it gains about 30, maybe 40% energy gain over what you started with. In other words, if you come through and you factor in the costs for growing the corn, the costs for processing the corn into ethanol, all the fossil fuel that's burned in processing it, you end up with about a 40% gain. It's not very much. Now the problem is that when you harvest that material, about 80% of the biomass, you're only harvesting the grain. And the grain's about 20%, and this is where the plant breeders have done such an excellent job, is to actually get it to be 20% of the biomass was pretty phenomenal. But 80% of the biomass is left behind. Some of it has to be left behind for maintaining soil quality. But there is a significant amount of material here that could be converted into fuels. The process is not too dissimilar to what you have for corn. In corn, what you do is you come through, and now that I'm in the business world, I start looking at costs. Corn right now is about $6 a bushel. You get 2.7 gallons of ethanol per bushel of corn, and it translates to about $2.22 of your feedstock cost. That's how much your grain costs you. The enzymes are cheap, and I'll show you why in a minute. The fermentation and distillation is inexpensive because you can get very high ethanol concentration. But with all of this put together, it's $2.50 to make ethanol, and right now it's selling for in the neighborhood of $2.50, i.e. the guys that are making ethanol are not making any money right now. Now the alternative is using some form of biomass. It can be an agricultural product, it can be a dedicated energy crop, it can be some kind of waste product here. These feedstocks are much, much cheaper. All right? Where the costs come in are in the processing. A pre-treatment is something that you use to open up the material, to make it more digestible. You want to separate it into the core constituents of the material, and it's costing more than $1 per gallon of ethanol. The enzymes are another major cost factor. They're costing more than a gallon per gallon of ethanol. Your fermentation and distillation is expensive because there are inhibitors that are inherent in the process that make it very difficult to get high beer concentrations. And so the end result is that to make ethanol from any kind of cellulosic right now is in the neighborhood of $3.44 per gallon. And clearly, if you're selling something for $2.50, you're going to need a whole bunch of help to make it happen. All right. So I'm going to skip by this for time's sake. So the end result is that you can actually make quite a bit. There are going to be some low-yield crops because this is the density issue that Steve was talking about. And that is that you can only harvest about 1 ton to 2 tons of dry matter from a field from wheat, other than the grain, and convert that into ethanol. So that yield is someplace between 100 and 150 gallons per acre. If you look at corn stover, this is everything but the grain, you can produce about 240 gallons per acre. And then you come to the energy crops. Switchgrass, sweet sorghum is actually coming up as a much a popular alternative. And these you can produce upwards of 800 gallons per acre. And then there are forestry byproducts that you can produce where you can get 1,000 gallons an acre. If you add up all of the capability in this country, you can make 60 billion gallons of renewable fuel each year, which would be a huge benefit. All right. So why aren't we doing that? The problem really has to do with infrastructure. Infrastructure because you have to have a source for the material that you're going to process. You have to have a collection means to bring it into a factory. You have to have a technology to convert it, and you have to build the plants to use that technology. The end result is that there's a lot of work to be done before any of this comes online. These are in order of what we consider to be opportunities. For the case of waste paper, what we're talking about here is the stuff that's not getting recycled. In the United States, we love paper. We go through about 750 pounds of paper per person per year in this country. About half of it gets recycled. Most of that is ending up in China these days, believe it or not. and the rest of it ends up in landfill. In landfills, it gets converted into methane gas. Methane gas is about 24-fold worse greenhouse gas than CO2. So we have a technology where we can recover the waste paper from a waste stream that's going to a landfill. This is actually something that's in place. What's missing is the technology, and we actually have a plant that's half built. Then there are a variety of other agricultural waste products. These corn fiber is something that's a leftover product from making corn ethanol. Corn cobs everybody's familiar with. This could be wheat straw, sugar beet pulp, sugarcane biogas, any sorts of things like this. And then you're going to have the energy crops. The things on energy crops is they take time to get them started. If you're talking about a tree plantation, it's 5 to 10 years before you're ready to harvest that tree plantation. If you're growing switch glass, it's 3 years before you have any large level of harvesting from that particular field. So the end result is that there's a lot of time before this gets developed. Now the uniform theme here is that in all cases you have to end up with a technology. And the one thing that I will tell you is there's no perfect technology. There will be no one technology to do this. I'm going to talk about one type of application, but I don't have time to talk about all of them. All right. So the application I'm going to talk about is something called an enzyme approach to digesting the material. This is going to be my simplistic model of what biomass looks like. I'll show you what cellulose is in a minute. The hemicellulose is surrounding the cellulose, and then you have a lignin as yet another barrier. These are barriers to processing. Most of your sugar is in the cellulose. The next fraction is in the hemicellulose. These, the yellow and the what should be blue, can be converted to fuel. The other ones, this is more like brown coal. So what you do is you pre-treat this. Now you come through, you add in enzymes. What the enzymes do is digest this material. You convert it into the core sugars. Some of them are 6-carbon sugars, some of them are 5-carbon sugars, and then you get lignin, which is brown coal. This can be used to fire the plants. This is why this has a large energy gain. This is what provides the heat for the plant. And what you can do is you can produce ethanol someplace between 64 and 85 gallons per ton, depending on how efficiently you're converting the 5-carbon sugars. And as I pointed out to you, the problem is that you have a high production cost. But the target that's being mandated by the U.S. government is that we drive the cost down to about $1.50. And if we can get the price down to $1.50, this will be competitive against gasoline. Actually, $2.50 will be competitive against gasoline. Ethanol has about 70% of the energy content of gasoline. So if you want to compete with gasoline, you have to sell it for about 70%. All right, a little bit of the technical side. When you process starch, starch is chemically simple. It's simply linked glucose. It requires 2 enzymes to process this. And this is why the enzymes cost 4 cents. They're easy to produce, they're stable, you can work with them for a long period of time, and therefore it's real easy to process this. This is why the corn industry developed to the scale it is. When you look at biomass, what you got is something that's very complex. I showed you the simplistic model. Here's cellulose, here's the hemicellulose, and here's the lignin. This is still simplistic. What you got is cellulose, it's depicted down here. This is about 60% crystalline. That means that the molecules are so tightly packed together that you can't get the enzymes into the material. Part of it is amorphic. Surrounding the cellulose is the hemicellulose. It's a mixture of different sugars. This is one component. This is a 5-carbon sugar sitting here, a different 5-carbon sugar labeled with A, and you can see that there's a lot of branching on this and such. So the end result is that this is difficult to digest. It protects this material. And then finally you've got that lignin fraction there that comes through, and it's more like a tar that coats the whole thing and prevents anything from getting into it. Plants evolved over the last 2 billion years to resist digestion. That's why they can be out there for as long as they can be. So what we're trying to do is reverse that process, to come through and rapidly release those core sugars. Now, the challenges are, first of all, the complexity of the material, but the other is inherent to the process. The limiting factor is the beer that you can produce. The beer is what you make after the fermentation, and you have to have at least 8% alcohol in that mixture, and the reason has to do with the energy input for distillation. The weaker the alcohol content, the more energy you have to add. Think about boiling water. The less water you have, the easier it is to heat up the system. The break-even point is about 8% ethanol. To get 8% ethanol, you have to have a high solids content. That means 15% solids. If you've had oatmeal in the morning, think about that. It's about 10% solids. So you're looking at something that is really thick, viscous, hard to work with, and that's what you're talking about here. So you're going to make some mixture that looks kind of like oatmeal, and now you're going to process it with a pretreatment and digestion, release the sugars, ferment that, create your beer, distill it out, and all do that for less than $2.50. The other thing is you've got a cost sitting up here. So you've got someplace like $1.50 to do the whole job. Now, as I pointed out early on, one of the major factors are the enzymes themselves. The enzymes are what are going to be releasing these sugars, and if you can do that efficiently and inexpensively, now you make this an economically viable process. For those of you that aren't biochemists, this is a crystal structure of an enzyme. You can see that there's a little groove in here. What you can do is you take a polymer like this, it will sit down in this groove. This catalyzes the cleavage of one of these bonds, in this case this one right here. The end result is that you end up with a 2 sugar and a 4 sugar in this particular case. This is what an enzyme will do. Enzymes are very specific. This enzyme will only cleave that bond there. It might cleave this one, and this one, but it won't cleave this one. This is still the same basic molecule. If you have a different set of sugars, you need a different enzyme to carry out this process. So it requires a lot of enzymes to do the job. Now, there are lots of very traditional places you can go out and find enzymes. All you have to do is look at one of two things. An organism that eats cellulose has to be able to break it down. It's usually not the organism that you're looking at that's breaking down the cellulose. Instead, it's a microbial community that's in the gut. So if you think about a cow or any other ruminant that's eating grass or any other plant material, in their stomach, they're harboring a community of microorganisms that are releasing enzymes and digesting the process. Those enzymes each organism within the system is a specialist. It can degrade part of the material, but not all of the material. So that's why you have a community, because each one does a small part of the job, and the end result is you process the material. But if you look at what comes out the hind end, and think back of what you learned as a kid when somebody was growing up on the prairie, you don't process it very well. You end up with a lot of leftover cellulose in a cow pie. They used to burn it as fuel, and in some places in the world, they still burn it as fuel because there's so much cellulose left during the residence time in the gut that it's a very inefficient process. Termites are another organism that you could think of that would process cellulose. Hopefully you've never had the misfortune of dealing with them. I once discovered 6 feet of load-bearing wall in my house was dust. It was not fun. So anyway, termites are an organism that will eat cellulose, but it's not the termites themselves that are processing the cellulose. Same thing. It's a community of microorganisms in the gut of the termite that are processing that cellulose. Each of those organisms are specialists, each releasing a subset of enzymes. You go to a tree, think about how long it would take for this tree to rot. It does eventually rot, but what you have is a succession of microorganisms that process it. Same thing for any kind of compost that you look at. So, but what all of these organisms are doing is exactly the same thing you want to do for biomass or biofuels production. The only thing is that these processes are slow. It requires multiple organisms to produce those enzymes, and it takes a lot of work to get through that process. So you end up with any of the sources of enzymes that you derive from here tend to be very expensive. The other problem is these enzymes tend to be slow. Each enzyme has to have the substrate bind to the enzyme, carry out catalysis, and release the product. It takes time. That means that because these enzymes are slow, it needs a lot more enzyme required to do your unit of work, and that is release sugars. These enzymes are sensitive. Most of them these days are coming from fungi. And most of the preparations actually have a history. If you've ever worn stonewashed jeans, it's a misnomer. They're not stonewashed jeans. They're enzyme-treated jeans. And they treat the cotton, which is cellulose, with enzymes to digest it. The commercial preparations in use today are byproducts of that process. But they're very sensitive to inhibitors that come from biomass, and they're also sensitive to ethanol in the process. The other thing is, as I said, microorganisms are specialists. They only release a subset of the enzymes to digest the material. And finally, they're really expensive to produce. All right. So where I come into the picture is that in my academic lab, we were studying this bacterium that lives in the Chesapeake Bay. And the academic question was, you're living in an infinitely large diluent. You eat by dissolving your food. How is it that you vector carbon back to yourself? All right? So what we found is that there was this bacterium here that had a remarkable ability to process whole plant material. We were able to convince the Department of Energy to do the genome sequence, and what was amazing out of this was about 10% of the genome was devoted to the processing of complex polysaccharides, and that translated to about 400 enzymes. Now, what was even more amazing is what this bug could do. This is the bacterium growing on the Washington Post. This is the only carbon source in the flask. This is what it looks like 24 hours later. It's basically gone. This is just the bacteria causing the turbidity. You can take the bacteria and put it on corn leaves. This is a chunk about this big. This is 3 to 5 days later. It's basically the waxy layers from the surface of the cells that are left. As we went through and looked at this, we found that we had a commercial application. This is where the company comes from. And what was really remarkable were the enzyme mixtures. These are 20 enzymes that attack cellulose. It's a very complicated process. If you add up all of these numbers, there are in the neighborhood of 50 enzymes that attack the hemicellulose and the pectic component, which are the other component of the cell walls. And there were even lignanases that allowed us to penetrate this process. So what it gave us was a one-stop shop where we could come through and produce the enzymes needed to digest this material into its core sugars. So what we were able to do at the company is develop some products that have application in this industry. As I said, pretreatments break up the material. You can get the brown coal component, the hemicellulose, which is predominantly 5-carbon sugars, and the cellulose components, and then these enzyme products are there to help digest the material. So I don't want to go into a lot of detail on this one because your interest has to do with really how do you produce the material. So what we have are enzyme mixtures. What we produce are very crude mixtures. We're not doing anything to purify these enzymes because it just adds too much for cost. What we have are much higher activities than what other people have seen. It's a very simple production process. We have a long shelf life. These enzymes, you can actually make the preparation, come back 2 weeks later, and have most of your activity left. That gives you a way to produce it and use it. Finally, we're using a non-genetically modified organism to make these enzymes, so that allows us to go into certain markets, such as food applications. And it's very safe to produce and use because there are some, it's not a human pathogen and no plant pathology with it either. So anyhow, I've talked on for a long time. I hope I've given you some feel for what the future of biofuels are in terms of using cellulosic materials. It's been mandated that 21 billion gallons of fuel be made from some advanced source. The only thing that right now meets that criterion for which there's enough feedstock is a cellulosic. So that it looks like something along these lines is going to be what is going to start displacing gasoline use in this country. I want to acknowledge Ron Weiner, who was one of the pioneers for working on sacrificious degradants. Everyone else on this list was heavily involved in doing some of the sequence analysis on the organism, working with a lot of the enzymes. Believe it or not, I didn't talk any about our academic work. As a microbial geneticist, I've learned that as soon as I say that word, it'll glaze people's eyes over. So I don't talk much about the particulars about what goes on. So I'll be happy to answer any questions.
Thank you, Steve, very much. That's another intriguing look at the underlying science and technology involved in what may be the future of the country. Let me turn now to Paulo Sotero, who will give us a Brazilian perspective.
I am a journalist, and I use PowerPoint because I like it. But I don't know how to put it on. It's a problem.
Escape first.
There tends to be a generational divide here with regard to technology use, I've noticed.
What was the title of your talk?
It is, if you show there. Yeah. And we can move from the first one. Let me put it on. How do you do this?
That's just before and after.
Yes.
All right. Let's get you. There you go.
Well, thank you very much. I'm going to tell you a very short and small story about this whole biofuels world. It's the Brazilian experience with this. Those slides come from presentations that were made here at the Wilson Center by two institutions. One is economists, which is a research institution in agricultural policy in Brazil. The other one is UNICA, which is a trade association for the sugarcane industry, especially for the ethanol industry. In Brazil, I'm just back. I literally arrived this morning from São Paulo. I sense talking to people that this discussion about biofuels is getting people pretty frustrated and mad in Brazil, because it is something that in Brazil is believed to be pretty well done, successfully done. It's an experience, mature industry, 35 years old about. It started because of the first oil shock. After the first oil shock, it took Brazil a long time to get it right, and I think the industry and the government and the car industry all came together about 5 or 6 years ago. It's very successful because we believe in Brazil that we use the ideal plant to produce ethanol. The joke in Brazil nowadays is that men are created equal, but biofuels are not. They're created very different from one another, and depending on what your location, again, location is key to this. This is why I start with this map, because this map shows the Brazilian biomes. The green one is the largest one, about half of our territory, the Amazon. The blue one is the Cerrado area. That's where agriculture is really happening, expanding in Brazil. This is a savanna. The light blue one is the northeast of Brazil. It's a dry area. That's where actually sugarcane started in Brazil. It started there. Whoever planted it first knew that sugarcane would do best in areas that have a long dry spell of weather, because that's what produces sugar in sugarcane. This other area, the Mata Atlântica, is the traditional area, the most developed area in Brazil. It used to be a forest. 7% of it remains, in comparison to 83% of the Amazon that remains as forest. The yellow one is Pantanal, is the largest wetland in the globe. And you have the beginning of the Pampa region here in Rio Grande do Sul, the southernmost state. I want to tell you where sugarcane is located in Brazil. Sugarcane started right here in the northeast of Brazil. Slavery started here with sugarcane. It's the oldest economic activity in Brazil. This is produces today both sugar and ethanol, but mostly sugar for export. The ethanol industry is basically located in São Paulo, is moving to Minas Gerais, is moving to the states of Mato Grosso do Sul and Mato Grosso. In this region, there are exactly 2 plantations of sugar cane. One around here in the state of Amazonas, owned by Coca-Cola to produce sugar, not ethanol. Probably one day they will learn that they could come south and produce much higher yields of sugar. Another one here in the state of Rondônia. And maybe one day they will realize that they should move from this area to other areas because their yields are not going to be very good here. They should move south. But this is to show you this from here. The sugar cane is expanding in this area, near the center of production and consumption. This from here to there is 2,500 kilometers. So if you hear from people that the sugar cane ethanol industry in Brazil threatens the Amazon, the answer you will hear from the industry, from UNICA, is that if not a single stick of sugar cane was ever planted in Brazil, the Amazon would be having the exact same problems it's having now, today, which is very much in the headlines. It's illustrated by, 2 days ago, the decision of Marina Silva, the Minister of the Environment, to resign. It is a fight for environmental protection of the Amazon and development. Nothing to do with sugar cane. Some people will say there are indirect impacts, like sugar cane is pushing cattle north in Brazil. There have been lots of studies done, non-conclusive. Probably soybean may be having that effect. Other crops in this area may be having that effect. Not ethanol, it's not clear. What we know about the Amazon has 2 major problems, not related to ethanol. It's related to lawlessness, lack of enforcement, lack of a policy. The second, involving that land titling is a mess. 50% of the land in this region is disputed land. 80% of all deforestation, as plenty of zone, happens in federal land. People the news in Brazil. 80% of our electricity in Brazil comes from hydro. But when you put together the whole energy picture, ethanol, sugarcane ethanol, has just surpassed hydro as a source of renewable energy. Why? Because in addition to using sugar cane to produce ethanol and sugar, one of the uses of the biomass, we burn part of the biomass to run the mills, and the mills produce a lot of electricity to run itself and it goes into the grid. This is going to be a challenge in the future because also in Brazil there is lots of research involving cellulosic ethanol, and many scientists say that, well, once you press the sugarcane stick, that's an excellent cellulosic material to produce more ethanol. It's already done. We know how to do it in one of the types of using one of the carbons, I think it's the 5 carbon sugars in the cellulosic material. There are estimates in Brazil that we could, once we know how to do this, to transform the cellulosic material in more ethanol, that we could increase our production of ethanol in about 50% using the same acreage without planting a single new stick of sugarcane. The energy balance of sugarcane, this is something obviously if you go to Brazil and you talk about this, people will point this out. Sugarcane is a very efficient plant to produce this type of energy, ethanol, and here you have the comparisons, the energy balance. So the idea is that for each unit of fossil fuel that you use, or equivalent, you produce this much. Obviously, once cellulosic ethanol comes into play, I think those numbers here will get much better. But this is what happens right now. The average production yields of the different liters per hectare, you can see there what happens in sugarcane and in the other plants used in different parts of the world. The ethanol demand is up with flex fuel vehicles. This is an important thing. If you go to a gas station in Brazil, we have some 33,000 of them. I think there was, a professor was talking about this infrastructure. This is solved in Brazil. You go to gas stations and you have gasoline and you have ethanol, and because the industry developed the flex fuel, and basically all cars being sold in Brazil now are flex fuel, you pick and choose whatever you want. And there is a difference in price because states in Brazil tax fuel in different ways. So you choose at the pump. And in big cities, in São Paulo, you can choose actually between ethanol, diesel, gasoline, and natural gas. Natural gas is used by taxis, by vans, and commercial transportation. Well, half of the consumption of light fuels for vehicles in Brazil today is ethanol. Those are some. Let me go quickly to, there is something that comes later, but let me, I think, since I showed you this, this consumption of fuels in Brazil, half is ethanol. Brazil was able to replace half of its consumption of fossil fuel using about 1.5% of its arable land, or 3% of land in use in Brazil. This is something about land use which is so important to this equation. This is a very recent research done by economists. This is outside of the Amazon. This is in the areas outside of that green. Okay? And it may be a little bit of arrogance on the part of Brazilians, but we say in Brazil that the food and fuel tension is real in the rest of the world. It is not in Brazil. In Brazil, we managed to build the ethanol industry while expanding agriculture and becoming the second or third largest producer and exporter of most commodities. Because Brazil has land availability. Right now, Brazil has land outside of the Amazon, the biomass, the biome of the Amazon. We have about 36 million hectares of land that is not in agriculture. This is in excess of pastures areas outside of the Amazon, and this is according to the industry where sugarcane should expand into degraded land. Sugarcane is planted in São Paulo and in the area where it's prevalent today in old coffee plantations. There was deforestation once, 200 years ago. Sugarcane replaced coffee. And if the projections of the industry are correct, it should move into pastures. We have in Brazil the largest cattle herd in the world. We have less than 1 cow per hectare. We could put 3 or 4 cows per hectare, continue to do organic, produce organic meat, and free a lot of land for other uses. This is a matter of public policy, this is a matter of incentives, but this is the current picture in the states that are outside of the Amazon region and are centers of agricultural production. Here are the areas that are ideally suited to produce ethanol from sugarcane, maybe 100 countries. You could expand biofuels production guided by good public policies for the reasons the two professors mentioned. It's very important that it's very well done, very well guided. But you could expand biofuels production to 200 nations, which compares to, you know, the current dependence on 20 oil producing nations. Well, Brazil is going to have a challenge on this whole debate because, as you know, Brazil has recently found a bunch of oil. So I'm curious to see how the governments in the future in Brazil will do all this, you know, highlighting our biofuels when we may become, in 10 to 15 years, the largest producer and maybe one of the top exporters of oil products, gas, in the Americas. I'll stop here, and maybe if you have questions, I'll try to answer them.
Terrific panel discussion. Let's go quickly to questions, and we will have a coffee break in a few minutes. The gentleman over there, it's appropriate enough, sitting right by a picture of Woodrow Wilson.
Oh, yeah. It's an honor. As Paulo, I'm also a journalist from Brazil, maybe from the PowerPoint generation, and currently a congressional fellow here in Washington. My question goes to Professor Hutchinson. Hutchinson? If I'm not pronouncing your name correctly, sorry.
That's fine.
Yeah. You mentioned, Professor, the problems of with corn here regarding food versus energy, and also the energy gain. But in some briefings and hearings I've been attending, some people also mention the questions related to emissions and water use. I wonder if you could also expand a little bit on that. And also regarding this map we are seeing right now, we see there, if I'm not mistaken, an area, small area in the United States where you could plant sugarcane, and I wonder why you didn't show sugarcane also in the United States as one of the possibilities here to produce ethanol.
Okay. The last question is the easiest to answer, and that is, let me go back to what the thesis that I opened up with, scale. So to produce enough fuel to do the job requires massive amounts of the material that you're starting out with. The misfortune of the United States is that we don't have a lot of territory to grow sugarcane. Sugarcane is by far the best way that I know of to make ethanol. It has a high sugar content. There's a expanding group interested in sweet sorghum. That would be another way to make a related compound, but sugarcane can only be grown in very limited parts of the states. And so when you look at it, it doesn't pay to put a lot of emphasis on sugarcane. We have to take advantage of what we can grow well. Now, in terms of the other issues on the corn industry, you can I wanted to point out that there's a lot of debate versus consumption of corn for fuel versus for food. And I'm definitely of the frame of mind that we should cap production of ethanol from corn with the existing plants that we have, because we don't want to put too much more pressure on that food source. It's a commodity that is being used for food and for fuel. But it has served an incredibly valuable part in helping this industry develop. We would not be here without corn-based ethanol. Corn has its negative components to it. One is that it's putting another pressure on the commodity. Number two is how you carry out the process, and water is one of the components on it. Growing corn and also the agricultural products. Corn requires a lot of fertilizer to be able to grow it. It's a cost factor in the process. In the plants themselves that are producing ethanol, they consume a large amount of water. Most of these plants have started to look at that as a way to improve their economics Most of them have relatively extensive wastewater treatment facilities. As an industry develops, unfortunately, we look at the situation where when water is cheap and grain is cheap, you go and you can. There's a good price for ethanol, then you go with whatever is cheapest to produce it. As the economics squeeze it, then you come through and look at what's necessary to improve the process to make it more economically viable. Now, did I leave out anything on your questions? Emissions. So emissions is an interesting topic, and I didn't mention that because one of the things to get into is how do you roll out a biofuel? Right now, ethanol has a rather substantial market, and that is as an oxygenated gasoline. And most of you are burning about 10% ethanol in your vehicles. And it serves a very useful purpose in reducing overall certain types of emissions from gasoline vehicles. There have been some studies come out that say that you can go as high as 30% ethanol into fuel and maintain the same mileage for the vehicle and have reduced emissions. A lot will also depend on how engines develop. Right now our engines are all designed to burn gasoline. All right? Ethanol has a much higher octane rating than gasoline, so that there's a lot of benefits for using ethanol, but the only vehicles right now that really burn ethanol are Indy 500 vehicles. All right? As engines get more efficient, then you're going to reduce some of the other hydrocarbon effects that you get from inefficient combustion. And as the industry develops, then you're going to have engines designed to specifically burn ethanol, following the lead of the Brazilians, who I might compliment you was a brilliant move. End up with vehicles then that efficiently burn ethanol and will end up with low emissions and a renewable fuel with minimal environmental impact.
Let me just return the compliment because, yes, there are a bunch of Brazilian scientists involved in this, but the companies that develop the engines and produce the cars are the very Brazilian Ford Motor Company, General Motors, Toyota, Honda, Volkswagen. So your companies know how to do this.
I want to also point out, I've been on road for most of the last month. And a while back, GM was talking about their forays into this particular arena. They're planning to have 50% of their fleet be flex fuel compatible in less than 5 years. So there is a move in a very large way to start addressing biofuels and particularly ethanol in this country.
Yes, as I look at the map, there's a large area of interior Africa where production of cassava is normal and where the cost of imported oil is very expensive. How does cassava shape up as a fuel stock for ethanol? Anyone who knows?
Again, it's on a regional basis. Cassava produces carbon. I work in sub-Saharan Africa. I'm not encouraging cassava production for ethanol. It's a primary food source.
Yeah.
And you don't think there's enough acreage there to do both?
No.
Yeah.
There's not enough water. There's plenty of acreage.
Yeah. And the other, I don't know. I haven't looked at cassava. It depends on how much tonnage of cassava you can produce per acre. And so if you can get the tonnage up and you can actually grow it, you can usually, as a rough rule of thumb, look at 80 gallons of ethanol per ton of material that you work with. Usually it's done on a dry ton basis, though.
We're running a little late. I'm going to make the last two questions there, and back the gentleman and then the lady.
More of a
If you could identify yourself and your institutional.
Larry Walker, Cornell University. It's more of a comment. The question about cost and availability of food. This is part of the debate. And you got to separate availability from cost, because there's some other dynamics going on with the cost of agriculture. I was looking at some numbers last week. Energy costs for agricultural production have gone up from 5 to 15% over the last 5 to 7 years. That's just the energy cost. And then if you look at the energy input in agriculture, about 45% of that is fertilizer. And fertilizer costs have dropped up very dramatically over the last 5 years for a very simple reason. Fertilizers are made from natural gas. And so you're looking at the cost of energy playing into the cost of commodities. And it's not just a question of availability. So I want to make sure we make that distinction between availability versus
Oh,
cost.
absolutely. And in fact, if you look at the increase in U.S. corn production last year, it was threefold higher than the increase in consumption for what went into corn ethanol. But the end result is it's still going to have an impact. You're still consuming a large part of your crop in this one particular application. And so, yes, energy costs are having an impact. People are talking about hedge investors coming in and buying it on commodities. No, you cannot account for the current increase in the price of corn simply because it's being converted into fuel. You're absolutely right.
I had a question related to the engine technologies.
Please introduce yourself.
Oh,
to
sorry.
everyone.
Priya Sridharan, National Academy of Sciences. The comment that you had made about engine technologies, I guess my understanding is that the modifications that are needed are relatively simple and more in terms of sensors and control algorithms and such, as opposed to real fundamental engine design, which would allow you to burn more ethanol. Can you talk a little bit about that, since you started to mention technology?
All I can do is I am not a combustion engineer or chemical engineer in any sense of the definition. I can only convey what I've heard being mentioned by automobile companies and the like. You can take current vehicles and convert them to ethanol use. But the design of the chamber that can burn that fuel has evolved, over the last 50 years to be much more efficient. Just look at what's happened with gasoline mileage for vehicles as you have optimized engines to work with gasoline. I imagine that the same thing can happen with ethanol. It is a slightly different fuel. It has a higher octane rating. That means you can burn it differently in the chamber, and therefore, as you optimize it, they say that you can get, if you optimize engine use, you can get ethanol to be as much as 80% as efficient as gasoline. Right now, we're running someplace, as I understand it, 65 to 70% as efficient as gasoline. So there's room for improvement. Whether how much that improvement is and how it takes place, I'm not going to be able to comment on.
Yeah, on this question, by coincidence, 2 days ago in São Paulo, I was at a conference, and someone from Embrapa is the Federal Research Agricultural Agency in Brazil, employs 1,500 scientists. They developed 500 different types of stocks of sugar cane, adapt to different soils, etc., and other things in Brazilian agriculture. And this gentleman told me that Embrapa, working with some Brazilian engineers, developed a prototype of a new engine that would be designed for ethanol. It's not the flex fuel, it's drawn from scratch. So, and I would like to actually put you in touch with him, because being from the National Academy of Sciences, you probably would know much better what the gentleman is talking about than I do. The other thing I wanted to tell you, one story that, as far as Brazil is concerned, is very important. And I think when you look at the map, this is the developing world mostly we're talking about. Ethanol, which, as I mentioned initially, is associated with slavery in Brazil. As you know, Brazil is one of the most unequal societies on earth. Getting better, improving, but still unequal. This industry started with workers' exploitation. Actually, there are many musics in Brazil to celebrate the boias frias, which are the workers to do the manual cutting of this thing, of sugarcane. Well, thanks to pressures brought about by democracy, by labor, etc., this in the state of São Paulo today, organized by unions, the cutting, and now the cutting, the manual cutting is being phased out because the way, in order to allow workers to get into the fields, what they do is that they, when it's ready for harvest, they burn the field to burn the leaves. So you can go there, otherwise you're going to be cut all the time. Obviously, it's not a very smart idea because you produce pollution, air pollution, and the cities in this area started to complain because you have smoke all over the place for 4 months. So there is now, a few years back, the government of the state of São Paulo started to mandate the mechanical cutting of the harvesting of sugarcane, which has some disadvantages because of soil compactation and other things. But that's the policy. It is now estimated in another 5 to 7 years, all sugarcane in the state of São Paulo will be harvested by machine, which will create another problem. 100,000 people that are migrant workers that live off of this. And this has challenged everybody, including the industry, to find other occupations, to retrain people. You know, and as a citizen of Brazil, I'll tell you, this is, I think it's a social problem we should have, because I don't think that a human being has been programmed to cut sugar cane by hand. It's a brutal work, and but I like to give you this example because if you do this well, there are ways that you can contribute environmentally, that you can cover some of your fuel needs, and also, you know, do what, in my view, is the most important, that this improves the lives of people. And it has contributed to that. There are much more to be done, but I think it's one of the positive things this industry has done in Brazil.
Well, let me call for a break there. Steve Hutchinson mentioned a hedge fund in passing. As soon as we have a very brief coffee break and a little conversation, we're going to come back and listen to Runge Johnson. Now, that sounds like a hedge fund. It's actually Ford Runge and Rob Johnson, two outstanding students of the question of food and fuel. And they will bring a more policy-oriented perspective to the implications for U.S. policy and policy around the world. As we break, please join me in a round of applause for very insightful panel. Thank you. Very nice. Steve, thank you. My far right, your far left, I'm delighted to introduce C. Ford Runge, who prefers Ford. He's the Distinguished McKnight University Professor of Applied Economics and Law at the University of Minnesota. He also has an appointment at the Hubert Humphrey Institute of Public Affairs. I was, at one point in my life, worked for Hubert Humphrey, so it's wonderful to see the way his heritage lives on at the University of Minnesota. Ford has a distinguished publishing career. Again, I'm going to be very brief. You have his bio in front of you. He's had his hand in trade negotiations. He's worked on the Hill. And one of the things that leapt out to me, he, in addition to studying agriculture, he owns and operates a small farm in Wisconsin. So we can think of him as our resident man of the soil. To my right, to his left, is Robin S. Johnson, Rob Johnson, a very distinguished academic background and a great deal of work with Cargill, a whole host of leadership positions. He brings a very erudite, I would say, sense of the economic side as well as the scientific side of agriculture. And he is currently a teaching fellow at the University of Minnesota Hubert H. Humphrey Institute. I'm going to ask Ford to lead off and then let them divide this presentation as they wish. You all have copies, I think, of the Runge-Johnson paper, which will get you thinking, I hope, about the policy and economic implications and some of the sensitive trade-offs in the food-fuel equation. Ford, the floor is yours.
Thank you, Kent. Can everybody hear me okay? Thank you. Well, Kent, Robin and I don't have a hedge fund of our own, but if we did, we'd be shorting ethanol. So today what I'd like to talk with you about is the perspective that we bring to the biofuels discussion. First of all, I'd like to say we very much enjoyed the presentations this morning. And I think both of us have spent careers with enormous respect for both the public and private enterprise of agricultural technology and research and biotechnology. The careers that we've spent, however, have been largely focused on delivering these benefits to world markets. And so we've been involved in trade and economics and the politics of agriculture. And because of the kind of work that we do, which is not scientific research, our perspective involves balancing benefits and costs and finding ways to deliver the benefits of agricultural technology at the lowest possible cost. So that if there is a tension between what we will say and what we heard this morning, it is the problems posed by potential benefits, especially from cellulosic technologies, in years to come, and the costs that the innovation of these technologies have presented, especially in the here and now. In this respect, I would quote the learned philosopher Charlie Chan, who once observed that question without answer is like faraway water, no good for nearby fire. And we have many unanswered questions in the technology of biofuels, but we have some raging fires with which we need to deal. And the two in particular that we'll focus on this morning are challenges to food security and challenges to the environment. We've agreed to divide our discussion with a brief introduction on my part to some of these questions, and then I'm going to defer to my friend Rob, who has spent a lifetime thinking about food security and trade at Cargill, and then I'm going to come back and talk a little bit about some of the recent evidence being developed in the scientific literature related to the impacts of biofuels at current technological levels on the natural environment. So I suppose that our perspective is revealed by the title of our presentation. But what I'd like to do first of all is to just spend a few minutes talking about the policy structure surrounding biofuels in the United States. There are essentially four components to U.S. biofuels policy at the moment. The first is a 51 cent a gallon blender's credit, which is passed through to producers. The Farm Bill, which is imminent, reduces this from 51 cents a gallon to 45 cents a gallon. But it is still a substantial underwriting or subsidy to the production of biofuels. The second is a border or tariff measure, a 54 cent a gallon tariff on imported ethanol, most of which applies to Brazil because they are the major other producer in the world market. This it was also affected by the Farm Bill legislation because the tariff, which had been scheduled to expire in 2010, was extended to 2012. And it provides another type of insulation to the domestic industry from foreign competition. The third, and perhaps the most significant in the scheme of things, is the 36 billion gallon mandate for ethanol to be reached ostensibly by 2022, of which, as we heard this morning, 21 billion gallons are to be composed of some type of cellulosic feedstock. And finally, there have been a variety of substantial grants, $385 million in all thus far, in subsidies to cellulosic pilot plants, with more contained in the fine print, again, of the Farm Bill soon to pass. Although it's hard to count up all of the subsidies, work done by analysts at the International Institute for Sustainable Agriculture estimate that in 2007, U.S. support to biofuels totaled about $6 billion, and in the EU, the total was about $4.8 billion. And as I just said, there are some more to come in the pending Farm Bill legislation. Now, I think it would be absolutely fair and accurate to say that the impacts of these subsidies and the rapid expansion of the biofuels sector, which again, as we heard this morning, is expected to expand from about 7.5 billion gallons, twice that in just the next year, is not the only explanation for the increasing price of corn, or indeed for the increasing price of commodities worldwide. That's very true. On the other hand, it's, in my judgment as a professional economist, inconceivable to explain this run-up in prices without accounting, to some extent, for the role of biofuels. So they are a necessary but not sufficient basis for explaining the increase in prices. But that increase in prices has occurred is undeniable. Here are the Chicago Board of Trade cash prices for corn from 2004, 2006 to the most recent estimates. December futures are now at about, what, 630, 640? And this is, by any standards, a remarkable increase in the price of this feedstock, and it's the primary explanation for why the margins in the industry are effectively zero, and why, had we a hedge fund, we would be short ethanol. I'm not sure if we'd be long corn or not. And so this has triggered a variety of collateral effects. For example, the decision in the last crop year to plant anywhere from 15 to 20% more corn acres has taken acres out of soybeans, and that's driven a related increase in soybean prices. That may correct to some extent this year, although it's been a cold, wet spring in the Corn Belt, and that's putting upward pressure on corn prices today. But if we look globally at the impact on food prices, we can see fairly clearly what has been happening to the food price index. The left chart from FAO shows the increase in the food price index for 2006, the run-up in 2007, which is the black line, and the takeoff in the food price index in 2008. The food commodity price indices for various commodities are shown in the right-hand side, but the trend is very clear, particularly in the cereals and the fats and oils market. And that is why we read of the great discontent in countries that are reliant, especially for cereals in the diet and fats and oils for cooking purposes. The ratio of world cereal stocks to utilization, which is another key indicator of relative scarcity of these commodities, are all headed down. So that would suggest that one would be long on these commodities if one were speculating in them. But my primary concern, and what Rob's going to talk about in a minute, is really focused on the human impacts of these changes. A few weeks ago I was talking with a reporter about partitioning the causes of these food price increases to various attributions, and we talked about Mark Rosegrant's estimates at IFPRI suggesting that perhaps a third was due to weather and a third due to expanding demand in China and India, and perhaps a third to biofuels. No one knows for sure how to apportion these causes. But a point I tried to give great emphasis is that we can't do anything about the weather, and we don't want China and India and other developing countries to grow any more slowly. So what can we do something about? Well, we can do something about blenders' credits and mandates and tariffs to allow markets to begin to reveal accurately what the conditions are in the ethanol market and more broadly in the feedstock markets which feed the plants. So just in the last couple of weeks, FAO, which is preparing a major meeting in June of ministers to look at this crisis, has put together a list of countries in crisis requiring external food assistance. And this is some measure of the magnitude of the challenges that are being faced globally. In Africa, there are 21 countries divided into 3 categories: exceptional shortfalls in aggregate food production, widespread lack of access, and severe localized food insecurity. There is the list. In Asia, by the way, this is contained in the paper that you have available, there are 10 countries, again categorized by those 3 types. In Latin America, there are 5 such countries. And even Europe has not escaped the impact of this run-up in food prices and commodity prices. Moldova is also facing exceptional shortfalls in aggregate food production and supplies. So that food security impact is something that we are most concerned about. It takes away not at all for our enthusiasm, especially for moving to cellulosic feedstock alternatives. But we have problems here and now, and they cannot be divorced entirely from the decisions to subsidize, in our view, to excessive levels, the expansion of the biofuels industry in the United States. So I'm going to turn to Rob and let him expand on the food security issue, and then I'll come back in a few minutes to talk about some of the environmental and ecological impacts.
Thank you, Ford. You've given a good part of my talk already. Let's see if, whoops, this is what I was afraid of. They've queued up your talk.
Oh, well, we can queue up yours. I'll steal the rest of my thunder.
Yes, get that off the screen right away. While she's doing that, let me start with sort of the frame the debate. Who is to blame for high food prices? And Professor Walker, I think, teed this up very nicely by saying energy prices are going up. That's really driving the car as much as anything else. If you talk to the Renewable Fuels Association, they estimate that corn price increases account for only 4% of the surge in food prices. If you ask USDA, it's 20%. I think that's a very sterile kind of debate to have. As Ford suggested, we need to focus on that which we can control, which are the policy elements that are influencing the surge in food prices, and on the costs or consequences and how they are falling across the world. So, for example, there are 82 low-income food deficit countries around the world who import both food and fuel, and for whom the surge in energy and food prices simultaneously is doubling the pain. Senator Grassley likes to talk about $5 cornflakes and that corn is only a nickel of that $5. We're not concerned about the people who are paying $5 for cornflakes. We're concerned about people who have to buy food that is much closer to the commodity end of the spectrum. And just as one example, eggs, which are corn, soybean meal, and hardworking hens, egg prices are up 29% in the last year. Farm incomes, in spite of the rising energy costs and in spite of the rise in feed costs for the livestock sector, net farm income is up over 50% this year compared to last year. The perception of others. The Indian finance minister about 2 weeks ago characterized U.S. biofuels policy as a crime against humanity. So however you measure this question. I think debating how much food prices are being driven by energy prices or by commodity prices is to some extent missing the point. We can't control energy prices short term. As Ford said, we don't want to slow down the rate of growth in the developing countries because they need to raise their per capita incomes. Weather is a variable that we know is there. So what we have left to deal with are the policy instruments that are contributing to this situation. Let me start by talking about sort of the general notion of food security and how it's fit into the U.S. Policy debate. The simplest definition that I've found is access for all people at all times to enough food for an active, healthy life. What that points to are the barriers to achieving that, which the one barrier that we agree is not the case is whether the world's producing enough food. As Professor Walker said, the food is available. What gets in the way is poverty of low-income countries who get priced out of the market for limited foreign exchange reasons or because their incomes can't absorb the price increases. Trade barriers, which concentrate the burdens of adjustment excessively on world markets. And I'm going to contend U.S. biofuels policies. It's ironic that when the United States has dealt with the issue of food security, we have argued long and hard, and I've been among them over my 36-year career at Cargill, that self-sufficiency is not a key to food security, it is a barrier to food security. That opening markets, getting prices right, bringing trade barriers down, and getting government out of the role of distorting markets will increase food security. And so the question that I want to pose is, how does U.S. ethanol policy measure up against those criteria? And I'm going to suggest that it measures up poorly. We have subsidies for local production, but not for imports. We have tariffs on imports, and we have escalating mandates for usage. Before talking about those specific policies, I wanted to mention that it came up toward the end of the morning session, the notion of, as we saturate the E10 market, where biofuels are going to get additional growth here in the United States. There are policies in place to promote E85 usage, including a 30% credit to install pumps that will handle it. Currently, there's less than 1% of the fueling stations in the United States that are capable of handling E85. But more importantly, there is what's called a flexible fuel vehicle exception to the corporate average fuel economy standards. And what that means is that if you produce a flexible fuel vehicle, it's not subject to the CAFE standards for your fleet. So it shouldn't be surprising to any of us that most of the FFV vehicles that are being produced in the United States today are large SUVs because it's a way to continue to serve that market and not in effect adhere to the policy implicit in the CAFE standards. The International Institute for Sustainable Development has estimated that that's resulted in an increase of 1 billion gallons in gasoline use in the United States per year. On the cellulosic side, the Farm Bill that's currently working its way through Congress adds a new $1 per gallon subsidy for ethanol from cellulosic sources and builds on the promise that I'm characterizing here as scarcely credible. I thought this morning's presentations did a nice job of summarizing the challenges facing cellulosic. There is a huge collection challenge in the infrastructure. There is a huge concentration challenge, in other words, to take diffuse energy and make it dense enough to be economically transportable. And then there are, of course, the huge conversion challenges. I'd much prefer to see the kind of money that's going into cellulosic operating subsidies be spent on research into those issues, because if we could solve some of those problems, we'd speed up the transition. But the three policies that I want to concentrate on are the ones that Ford mentioned, 51 cent per gallon blender's credit, which incidentally went in place when oil was $30 a barrel and has remained unchanged even though oil prices have quadrupled. Congress, I think, is beginning to recognize that that's not a very sensible policy by reducing the blender's credit from 51 cents to 45 cents. They're directionally correct, but they're much too tentative in the policy change that's happening. I would argue, and I think the economics would show, that in the absence of that 51 cent a gallon blender's credit, ethanol producers couldn't bid $6 for corn to convert it to ethanol. The second policy, the 54 cent per gallon import duty, it reflects clearly a comparative disadvantage for corn-based ethanol versus sugar-based ethanol. And my question here is, if self-sufficiency is bad for food security, why isn't it bad for energy security? If we are truly interested in reducing our dependence on imported oil, why not import sugar-based ethanol? But I want to save most of my thunder for the escalating mandates under the Renewable Fuel Standard, which I think have both long-term and short-term adverse effects. Let's talk about the long-term real quickly. The 2007 policy change raised the mandate to 36 billion gallons by 2022, which, if met, means that the corn exportable surplus from the United States is by and large going to evaporate. We're using 25% of the corn crop this year to produce ethanol. It's estimated that to meet the mandate escalation, we'd have to divert 50% of the corn crop by 2015 into ethanol production. To me, that's hanging out a sign that says, importers beware of depending on the United States as a reliable supplier. And long term, that ought to be a source of real concern to the corn industry here in the United States. But it's the short-term problems that are really troubling, because they're the heart of today's food price debate. The switch from the 7.5 billion gallon mandate by 2012 to 36 billion gallons by 2022 raised the 2008 mandated usage from roughly 6 billion gallons to 9 billion gallons, a 50% increase in the mandated use this year over and above the 32% increase in usage of corn for ethanol in 2007. So we are essentially forcing a doubling of the production of biofuels in the teeth of a very tight global supply situation. This year's corn crop, I think, was 13.1 billion bushels. The national average yield was 151.5 bushels per acre. If you take the 51 cent per gallon blender's tax credit, what we are doing is paying over $200 per acre on average to divert corn from food uses to fuel uses. There's no additional demand being created now. We are in price rationing. That's what $6 corn tells you. And our policy is saying in that rationing environment, we'd prefer to pay $200 more for you to put that corn into fuel rather than into feed. Ford mentioned that roughly 12 million acres shifted out of soybeans and other crops into corn last year. The ethanol mandate for 2009 will be 11 billion gallons, up 2 billion more gallons from this year. So what is happening is that wheat and soybean have to bid for acres from corn in the face of yet another mandated increase. And that's why you're seeing not only corn prices at 6, but wheat and soybean prices at the unprecedented levels that they are at. I don't see how you can resist the conclusion that biofuels policies are undermining food security now and over time. And interestingly, there's growing recognition of that even in Congress. Kay Bailey Hutchinson has a bill to freeze the renewable fuel standard mandate. There are 24 senators who have asked the EPA to allow states to waive the mandate requirements on them. President Bush did request that we not extend the 54-cent import duty in the Farm Bill. That request was ignored by Congress. Congress has decided to reduce the blender's credit, directionally correct, but not enough. And there is a bill, H.R. 5911, to repeal all three of the ethanol policies that I've mentioned. This is a sea change in recognition and attitudes, and I think it's only going to accelerate. Let me conclude by just mentioning a couple of ideas that Ford will mention on different ways of dealing with this policy issue. First, we've suggested that rather than having a fixed subsidy for converting corn to ethanol, we have a variable subsidy linked to the price of corn. In other words, as the price of corn rises, the size of the subsidy declines and eventually goes to zero, so that fuel uses and food uses can compete whenever we are in an equilibrium marketplace, and that the subsidy for fuel use would only kick in when corn was in surplus. We agree with the calls for a freeze on the mandate. We think at 6 billion gallons that would be appropriate. That is, frankly, roughly the size of the oxygenate market, where ethanol does command a premium and would avoid some of the discounting that we've begun to see. We think the import duty ought to be phased out, and the savings from these policy changes ought to be put into research and development investigation of all alternative energy sources, biomass-based and others. Thank you.
Thank you, Ron. Ford, you had some additional thoughts.
I had just a few, and then we can open it up for discussion. This morning, I think quite correctly, Professor Kresovich observed that biology is complicated. I tell my classes that economics isn't complicated. It's just often very inconvenient. And I think many politicians, including Hillary Clinton, have expressed such a sentiment recently in connection with proposals such as the tax holiday. And some of the inconvenient truths that we've been talking about thus far are things that we need to begin to internalize and understand and act on. Now, I'm going to turn slightly from the discussion of food security, which in my judgment is a paramount concern, to another set of issues that are at least as important, but maybe more systemic, a longer run, although some of them will manifest themselves quite soon. And that has to do with the complex of environmental and ecological impacts of the biofuels sector. Now, for a long time, biofuels got a buy in this category of effects because it was argued, without a great deal of evidence, to be frank, that they were a green alternative to petroleum fuels. But there's an increasing body of research, I'm proud to say, some of it coming from the University of Minnesota and my many colleagues there, that is beginning to actually attempt to put numbers to an assessment of the life cycle impacts of the biofuel sector. And if there was some environmental equivalent to going short on ethanol, it would point us in the same direction. So let me talk for just a couple minutes about these issues. Let's first talk about water use. In a study published last year, the National Academy reported that corn grown for ethanol consumes about 200 times more water than is required to produce it and process it. So the production of the plant itself is enormously consumptive of water, and we've understood that for a long time. Processing, however, requires about 4 liters of water compared to about 1.5 liters per liter of gasoline. If there's any single effect that is of special concern to me, as someone who's worked and lived in the upper Midwest for most of my life, it is the impact of expansions in corn production, both in terms of acres that have traditionally been devoted to rotations of row crops, soybeans and corn, but even more so the extent to which corn is calling acres into production that were explicitly retired to the Conservation Reserve Program because they were deemed unsuitable for the production of maize or corn. And the consequences of this shift in cultural practices, which is being driven to a large extent by the biofuel sector, is going to impose loadings of both nitrogen and phosphorus into the lakes, rivers, and streams of the Mississippi watershed, as well, I might add, locally as the Chesapeake watershed, and others, that are going to have predictable impacts on the levels of eutrophication in these water bodies. That is to say, the depletion of oxygen in the waters. We know, for example, that a substantial share of the nitrogen and phosphorus that are loaded into the Gulf of Mexico have their origins above the confluence of the Ohio and Mississippi rivers. In other words, they come directly from the Corn Belt. If you know anything about corn production in Iowa, you know that about 98% of the arable acres of Iowa are underlain with complex tiles and drains, the purpose of which is explicitly to take the water off the field and put it into streams and rivers as rapidly as possible so as to facilitate planting early in the spring. So we have designed a system that is going to push these nutrients into the water bodies of the United States with predictable impacts on water quality. The dead zone in the Gulf is going to increase in size this year alone by 25%. Land use. As I mentioned, millions of acres are leaving the Conservation Reserve Program for corn and soybeans, both of which are erosive row crops that formed the basis in a low-price environment for the justification of the CRP first in the 1985 Farm Bill. And in many ways, those of us who lived through the 85 Farm Bill recall that in the midst of the farm crisis and the bankruptcy of the farm credit system, the CRP effectively proposed to rent millions of acres of land from farmers to the government to support what was then a collapsing farmland price. And although they weren't terribly well targeted at first, indeed I remember in 1985 land that I retired into the Conservation Reserve Program myself was paid a premium because it had been part of corn base. Well, what's that about? Well, it's not about erosion. It was about surplus production. So millions of acres are now coming back into production with predictable consequences. You know, with respect to the substitution effect, which we talked about this morning, even if we were to substitute just 10% of our petroleum fuel needs with biofuels, the estimate published in Science last year indicates that would require 43% of U.S. cropland and 38% of cropland in Europe. The reason that Brazil has been so successful, in part, although there are many reasons for its success in this area, is that it has and continues to have a huge, extensive margin into which to move the production of sugarcane. Very recently, in February, a widely quoted set of articles in Science magazine argued that corn for ethanol on converted cropland has the effect of creating a carbon debt. This article, which was largely authored by University of Minnesota scientists, had the immediate consequence of causing the soybean growers of Minnesota to eliminate a $2 million grant to the agronomy department for research. The soybean growers president indicated that the $2 million had been X'd out because we had hurt their feelings. After a kiss and make up session with the dean, they've restored funding to the university, but they remain hurt, I think. This carbon debt depends on the particular type of soil or forest cover that is converted and ranges based on that estimate from 98 years to 423 years in an extreme case of palm oil biodiesel produced from peatland rainforest. what the implication of this is that retiring the carbon debt created by land conversions to produce biofuels, depending on the type of land cover, suggests that if climate change and carbon loadings are indeed an imperative issue of policy, the benefits from biofuels consequent to this carbon debt will not be seen for maybe 100, perhaps as much as 400 years. So this flies in the face of the notion that we need to do something now. In the accompanying article, chief author of which was Tim Searchinger, formerly of Environmental Defense, in a relatively comprehensive attempt to find out how land use changes will be affected interactively around the world. The best way to think about this article is the notion that if you push a balloon in one place, it's going to punch out somewhere else, so that land conversions in one part of the world are going to affect land use in other parts of the world. He found that greenhouse gas emissions increased due to biofuels production over 30 years and continue to increase for 167 years. Even switchgrass has this effect on land use conversions, such that it increases greenhouse gas emissions by 50%. In what I think is probably the most compelling piece of work, Paul Crutzen, the Nobel Prize winner in chemistry at the Max Planck Institute, published a piece in the Journal of Atmospheric Chemistry and Physics late last year, suggesting that the nitrogen fertilizer used to grow the corn and rapeseed in his study necessary for biofuels would release enough nitric oxide, laughing gas actually, well it's not very funny, N2O into the atmosphere, and this as a greenhouse gas is 296 times more damaging than CO2, suggesting that these changes will be net greenhouse gas negative. So in working with the FAO, what I've done is to call for the development of impact matrices by country and by continent, looking at different feedstocks in relation to a whole set of criteria, so that we can begin to develop priorities and understand where we should be putting our emphasis, funds, research, and the like. And I won't belabor that. Let me just conclude by emphasizing the policy responses that Rob and I think are appropriate given these problems. To replace the 51 cent a gallon blender's credit with a subsidy that is inversely related to the price of corn. So, for example, if you were to set the base at $3 a bushel, which is a pretty good price, used to be at least, for corn, the credit would be 51 cents, but by the time the price had risen to $3.51, it would be zero. And the implication of this is that as corn became more dear, more expensive, and more scarce, you would not be rationing it away from food uses or feed uses for fuel. Secondly, we would phase out the 54 cent a gallon tariff on imported ethanol and impose a moratorium on mandates. In addition, we would introduce a much wider ranging set of negative pollution taxes and credits related not just to the biofuel sector, but to energy conservation and use broadly defined. And finally, as Rob mentioned, we would shift the subsidies and monies spent on these other instruments from cellulosic plants, which really have the effect of simply paying down the relative inefficiencies of those plants, to substantial investments in cellulosic research and development. So that's what we have to say about these things. We'd be happy to respond to any questions or concerns you might have. Thank you.
Well, thank you both. That was a terrific presentation. Let's open up for questions. Professor Hutchinson.
Hi.
We've got a microphone right there. Just introduce yourself for the web
Right.
audience.
I'm Steve Hutchison. I spoke earlier. So, and I, both excellent. The critical part on that process to get started was how do you convince the oil companies that dominated the fuel market to start using ethanol? And the only way to do that was the blender's credit. And the blender's credit is actually going to the blenders, not to the farmer and not to the producers. And in my mind, the money going to the blenders is the least useful aspect of that money. The second has to do with a correction. If you look at the 2007 energy bill, there is a subsidy going to cellulosic ethanol. But that subsidy is a variable subsidy. You said it was $1 a gallon, and it's not. It's hinged to the wholesale price of gasoline. The smaller the difference is between the wholesale price of gasoline and the price of ethanol, the smaller the subsidy. It's only when there is a large difference do you see, excuse me, the other way around. When it's a small difference, there's a large subsidy. When there is a large difference, there's a 25 cents a gallon. And the whole idea is to jumpstart that industry because, as I pointed out, it's very expensive to make cellulosic ethanol and to go out in the real world and raise money to build a company to carry out a process. You have to demonstrate that it's an economical process. And the only way to do it right now is with those credits. The question has to do with in your mind, how are we going to solve the problem of limited petroleum, and what are we going to use to solve the part that you left out, which is energy security? We're the most energy-intensive society in the planet. Half of the energy bill was devoted to conservation, but the other aspect has to be how we produce the energy. So clearly not producing it from a food product is a good idea, that we need to have some other way of doing it. But there are costs to doing any process. Where do you propose that we go from?
Sure, let me start. First off with the middle point. You may have noticed I had glasses on when I was doing my presentation. I can't read very well, and I missed the up to in my note on the dollar. So your correction there is well taken. Nice to see the principle of varying the subsidy at least is being recognized, and but the variation is tied to the wrong criteria in our view. Let me go to the first comment. You said it's clear we have to get off of petroleum. Clear to whom and for what reasons? There is ample supply of fossil-based fuels, not in the conventional sense of oil in the ground, but in the sense of coal that's available for liquefaction or gasification, oil, shale, tar sands, technologies that are accessible, at least according to the Resources for the Future, at a much lower cost than cellulosic ethanol. So the clarity that you express at least is open to some sort of question there. But let's say that we do need to find alternatives to fossil fuels. What kinds of criteria should we be using for the pursuit of that? Certainly, as Ford suggested, one of them ought to be that the effects on the environment are better than rather than worse than the effects of the existing energy sources. And that was another assumption made with respect to biofuels that at least needs to be questioned because the evidence is accumulating that was not a correct assumption. But secondly, if we are doing this for energy security reasons, then we get back to the question that I was trying to raise. What kind of a system produces energy security? Is it one that views the goal as national self-sufficiency, or is it one that views the goal as creating global markets that find the least cost alternative sources of supply and the most open markets to provide stable prices and secure access to supplies, or is it go it alone? And I personally am in the former camp, not the latter.
So, but I think that if you look at it, let's go back to any fossil fuel that you use. And my point for rise in CO2 in the atmosphere was that there has been an unprecedented increase in the rise in CO2 in the atmosphere, and it's projected to continue until at least 2050, if not more. If you look at the isotope composition of that CO2, it matches what's in the fossil fuel. Therefore, it's not something that's being leaked out of the oceans, but is actually due to human activities. All right? And that if you look at the current global temperatures in the United States, they match perfectly what's going on in atmospheric CO2 as being the front component. So in terms of environmental impacts, you start having trade-offs. It's clear that we have to do it in a way that's smart. And I think that it's important that you come through and factor in not only what's being consumed in that process, but and what's being produced, but also what's the long-term impacts of the alternatives. And that's what I'm seeing is being left off in this aspect, is that there are alternatives out there. They're expensive, they're limited, they're going to get more expensive, and they're coming from places that not necessarily we want to be buying from. I mean, we're funding basically our own increase in the price of gasoline just because of where it's coming from, and the fact that if you listen to the DOE, they say that the true price of gasoline is actually about $9 a gallon if you factor in national security aspects.
Well, let me just, I'll say quickly, and then we'll move to another question. I share your concerns about the loadings of CO2, and I would observe that that the Crutzen results indicating the loadings of N2O are even worse from the point of view of the problem that you're describing. I mean, 296 times worse, as a matter of fact. But you have raised a fundamental question, which I think really ought to guide a lot of our thinking about this area, and that is, do the existing subsidies, which are largely going to corn-based ethanol, I mean, there is not a gallon of cellulosic ethanol being produced commercially in the United States now, not a drop. Yep. Are these subsidies actually, as is often described, a pathway to a cellulosic future, or are they a barrier? My judgment is that by taking the steps that we've suggested here this morning, we will actually open the field more effectively to cellulosic research and development and alternatives. So I think that's a fundamental question. I don't know the exact answer to it. On the energy security side, I want to share with you something that's discussed in the paper. If one looks at the standard statistical measure of security, as it were, or risk, which is the coefficient of variation in a price series over time, and compares the coefficient of variation in the price of corn to the coefficient of variation in the price of petroleum, for example, from 1960 to 2005, the standard deviation in U.S. corn yields was 11.9, which is the square root of the coefficient of variation. The standard deviation of petroleum imports was 6.7, about half. Despite the fact that this included the period of the Six-Day War, the Arab oil embargo, the Iranian Revolution, and the Iran-Iraq War. So if one is looking for energy security, it's an open question whether or not one should shift one's portfolio in the direction of reliance on corn from petroleum or not. And I don't imagine you think we should. We're talking mainly about cellulosic alternatives. But we're up to our eyeballs in corn-based ethanol at the moment.
It's the only way you could do it.
Paulo, and then Larry. Yeah.
Thank you very much. Paulo Sotero from the Brazil Institute here. Mr. Johnson, I want to ask you a question. In February last year, Wally Tyner from Purdue University talking at an event we have here about the global dynamics of biofuels with Bruce Babcock and Marcos Young, was then at Econi, now at Unica in Brazil. This issue of finding a way of changing the blend, the tariff, the credit. He came up with a formula which would make that credit vary according to I think it's the price of oil.
It was.
Mm-hmm.
Yeah.
At that time, I think a bushel of corn was under 4, and the price of oil was probably 40. Barrel.
It'd be a little low, more like 70 probably. Yeah.
70 February. Now, I just wanted to understand how your proposal compares with his, because his was actually part of a bill that Senator Lugar introduced later on in the context of this cooperation between Brazil and the United States.
Purdue, Indiana, Lugar, Indiana.
Yes.
Yes, what we share is the notion that if there is to be a subsidy for biofuels, that it ought to vary. Where we differ is where the linkage should exist. We think that a linkage to the price of oil will lead to a worse situation with respect to food security than the one we have now. That as the price of oil goes up, you become even more dependent on corn-based ethanol because the incentive to convert that corn to ethanol is going up. So we're saying, go back to the origins of this corn-based ethanol policy. It was seen as a way not to purchase energy security. Synfuels were going to do that. Corn-based ethanol was sort of a little thing to help get rid of surpluses corn, originally created by the Soviet grain embargo and subsequently by just the structure of farm programs. And we're saying, actually, there is, given the variability in corn yields that Ford alluded to, some logic behind a subsidy that would increase when corn was in greater surplus. It would function more like a stabilizer for corn prices and supplies rather than what it is now, an amplifier of those prices and insecurity.
Let me just add one inconvenient aspect of the economics of corn and oil. During the period that the 6 billion gallon MTBE allowance was being filled by ethanol as MTBE was phased out, the prices of oil and corn and ethanol were moving in a way that you would expect of complements. That is to say, they were moving in opposite directions. But demand theory tells you that substitutes prices move together. And once that niche of the MTBE market of 6 billion gallons was filled, and it is filled now, the price of oil and corn have been moving together. And so over the last 24 months, roughly speaking, the technical term for this is the co-integration of the price series has revealed a substitute relationship. And what this really means is that the higher the price of oil, the more producers of ethanol can afford to pay for corn to convert it to ethanol. And that's the underlying reason behind Robin's point that if you have your variable subsidy tied to oil, what you're going to find is that you can't escape the fact that they're acting as substitutes and the prices are moving up together. Whereas if you decouple the price of oil from the blender's credit to corn and put it in terms of the corn price, then what you're doing, as he described, is you're providing the subsidy in a low price environment for corn, but you're reducing and eventually eliminating it as the price of corn reveals the fact that the market is in scarce supply, so that you are not rationing corn away from food and feed to fuel in a high price environment. I hope that's simple enough.
Larry? And please reintroduce yourself.
Again, Larry Walker, Cornell University. So I have a clarification and a comment and question. So my clarification goes to Professor Johnson. My comment about agriculture and energy was meant to kind of illustrate a point, not to convey that the price of food was only related to energy, but to other issues. Okay, energy is an important input into production agriculture. And I would agree with you that these other factors are playing a role in that. So that's my point of clarification. My concern is that we lump all biofuels in the same category. So I look at your title, you said the browning of biofuels. Well, when I look at biofuels, I'm not just looking at corn-based ethanol. I'm looking at cellulosic ethanol. I'm looking at methane production through anaerobic digestion. If you look at the Northeast and you go back 5 years ago, methane from landfills was the #1 renewable resource in the Northeast. Okay, and that did not take any crop, it was taking waste. So when you lump all biofuels in one category, I think you're doing a disservice to these other possibilities out there. Now, my question deals more with not the mandates, because I think actually we will probably be in more agreement than you realize in terms of this issue about subsidies. The issue becomes one, can the industry, can the technology keep up with this? Because it's one thing to set these mandates, to set these targets. I would argue we're going to be constrained from meeting these mandates because of our ability to bring these plants on as fast and bring the technology on fast as people are suggesting.
Let me take just some of the mandates first, and then you can.
Okay, go ahead.
Let me just say something very quickly about the mandates. Well, two things. First of all, of course, your point is very well taken that when we refer to the browning of biofuels, we're primarily concerned about the current almost exclusive reliance on corn or maize. And we are supporters of cellulosic alternatives, enthusiastic supporters, but we got to get the costs down. Now, here's the basic problem. You've got a set of capital investments in corn-based ethanol. And these capital investments have useful lives. They have vintage lives, as you might call them in capital theory, of anywhere from 15 to 20 years. They cannot be readily converted to, say, switchgrass. About 10% of a corn ethanol plant can be converted to switchgrass. So, you know, you're going to have to build the cellulosic plants de novo. Who's going to build a cellulosic plant based on switchgrass in any close vicinity to a corn-based plant and expect farmers to switch from corn to switchgrass at $6 corn? It's not going to happen. So the essential problem with producing the feedstocks for the cellulosic alternatives is that the corn-based plant regime is a barrier to that conversion. And that was the point I was trying to make earlier. And it is a serious problem.
I put up the tail end of our policy responses to just add to this. What we are saying is that if you take an approach that depends on large fixed subsidies, high import barriers, and escalating mandates, you are undermining the capacity of the market to do the two things that it does best, to calibrate relationships in price terms and to signal where innovation should occur. We prefer a strategy that concentrates resources on research into alternatives and bringing down the cost of alternatives to trying to promote the existing set that has been anointed as the future. We're no better at guessing which of these technologies at the end of the day is going to prove most cost effective. And so let's free up the market to perform the function it does best and devote the public resources to the research end that it's more likely to be a higher return on those dollars.
We have reached our witching hour. Did you want to have one
more question?
I will yield the floor to the distinguished gentleman from Cornell.
And it goes back to the study at Minnesota. So actually, Tillman has done two studies, the one in science this year and the one in last year. And you got me thinking about this with your comment about switchgrass. We tend to lock in on one specific feedstock or one specific cropping pattern. And as I heard my colleague Steve Kresovich talk about this morning, there are many of us who are talking about the role of polyculture in all of this, which was a big deal in the Tillman study last year.
Yes.
So if you do the polyculture angle on this, that carbon platform that was reported in Science this year has a totally different rate and extent component to it.
Yeah. That's an interesting point. Dave, I'm not going to speak for Dave Tillman, although I have spent many days at the Cedar Creek Ecological Research Station where this polyculture work is being conducted. Largely because my son was working out there this summer. but anyway,
Watching the grass grow?
I was just watching the grass grow. But the thing that Dave is trying to do is to optimize the biomass contribution together with the ecological integrity of stands of plant materials for the purposes of biofuels, and that's very, very important research. What dogs me and him is the fact that the current regime has still got corn prices, up at $6, and how are we going to persuade farmers to make the cultural conversions to these types of plant stands as long as these types of distortions persist? So I think that your point is extremely well taken, but I still think that our concerns with these policy distortions have the effect of trumping much of this good work.
But But again, those policy distortion is around corn-based ethanol.
Yes, it
By
is.
and large. And the only thing I'm asking for is more clarity in this discussion of biofuels around what's going on with corn-based, what are the issues there, what are the issues around lignocellulosic, and what are the issues around these other possibilities.
And that was the import of the matrix that I proposed, in which different feedstock alternatives were compared. Thank you, though.
Well, please join me in a round of applause for this outstanding talk. I think we've looked at the science, we've looked at the technology, we've looked at the economics and policy, and I think we've laid a basis for a conversation that will continue through this decade and well into the next. Thank you all for coming. We'll continue our series on science and technology.